And this is going to be a list of pairs, and this can be any size I need. So what I would do with this table is, let's handle duplicates to begin with. Okay, let's say that we have number 11, the hash of the number 11 could point to, well, let's put another Bob here. Okay, now it points to 4, but it could point to 4 or 8. So what we're going to do is have a new table over here where we have an index to point to. That's going to be this number, and not a hash, but just a, I'm just going to call it a pointer number. I'm not sure what to call it. But what we're going to do is, first of all, we have to have another piece of information in this table here. I'll just make another little column here. That's going to say, is there a collision and or is there duplicate names? And so we would have something here that indicates that, which means, okay, now we have to go to the second table. So here we have a data collision. So we have an indication of that. I'll just put a little X here. Something that says I have a duplicate name, go to the next table and deal with that. So we're going to deal with both Bobs right now. So let's get rid of Dan over here. Just 2 Bobs. Oops. Okay, how are we going to deal with that? Well, we're going to have something telling us that there's been a duplicate name. We could actually put that right here somehow. Some kind of code right in that spot there that says, okay, duplicate name, go to the next table. This is our first duplicate name, so we'll put the fix right at the top. So we have a hash of 11, and that would go to 4. But a hash of 11 might also go to 8. So that's resolved here. So we hash it out, Bob, 11, 11, oops. We're going to have to go resolve that. So let's go ahead and put that right here. Let's put that indication right there. So we can put that here because there's only 100 possibilities here, and a byte of information could hold 256 possibilities. So I can put some code there that says, oops, duplicate name, go to the duplicate name table. And so now we go there. All right, that could be 4, that could be 8. What do we do about that? Well, if I'm typing into a database, I want Bob, it's going to come, okay, here's 2 Bobs. Or how about another one? Let's put him, whatever. Let's get these guys out of the way. How about another Bob? Number 10. Okay, so, collision, 11 goes to also to 10. So now, what's going to happen, I say, I want to see Bob. Bob, tell me database, where is Bob? The database goes in there. Okay, it hashes Bob, comes out with 11. Multiplies that by 2, jumps down to here. Okay, number 11 goes to, duplicates. Go to the duplicate table. Okay, there's Bob 1, Bob 2, Bob 3. Here's your 3 Bobs. So it's going to show me all 3 Bobs. I have to decide which one is the right Bob. And that's just a common thing. You've been through that. You're searching for something, you get duplicate names. Here you go. Which one do you want? So this would be my list of duplicates. And notice I can have as many duplicates as I want. I just make the table bigger and bigger and bigger. So for example, let's say I get another Dan. Don't want to do Dan because he collides with Bob. Let's say we get another Jan. So that's going to be number 9. So we ask for Jan, give me Jan. Jan is hashed. Jan comes out to number 17. 17 now has 2 entities, so there's a marker saying, there's 2 Jans here, go to the duplicate table. And so number 17 is also going to go to, it's going to go to 5 and to 9. So we have duplicates here. We have 3 Bobs and 2 Jans. So Bob could be either 4, 8, or 10. So I search for Bob, Bob. Okay, 4, 8, and 10, Bob, Bob, Bob. Here's your data for this Bob, that Bob, and the other Bob. Which one do you want? Or I'm going to look for Jan. How about Jan? Hashes Jan, comes out with 17, jumps down, goes, there's a duplicate. Go to the duplicate table. 17 goes to 5 or 9. So grab 5, grab 9. There's your 2 Jans. You pick the one you want. So That is how it would handle duplicate names. And collisions would be handled pretty much the same way. And I'm trying to think, could I have this one table handle both duplicates and collisions? Maybe, because I don't want to have a situation where I type in, where's my problem? My problem is Dan. Dan is my collision. So actually, when it comes to names, so far that's both Bob and Dan. So I type in Bob, it says, oh, duplicate, go to the duplicate table, and it's going to give me Bob and Dan. Okay, Bob or Dan, which one do you want? What are you giving me Dan for? I wanted Bob. So I have a duplicate and a collision. Let's say there's something in here. I'll just put a little Y. Some data in here that can say this has a collision. I'm going to have handle them slightly differently because I'm going to not want to find every Bob and every Dan and present them. I'm going to have to filter out the Dans. So is there a quick and easy way to do that? Maybe. Of course, the computer can always say, okay, is it Bob or Dan? Let's go ahead and deal with that. So 11 could also be 7. That's a Dan. Okay. So 11 goes to 4. That's a Bob. Is that right? Probably the software could handle this at this point. I say, looking for Bob, goes in there, hashes Bob, gets the number 11, goes to 11, looks in the duplicate table, and says, okay, 11 goes to 4. That's Bob. Okay, I'll throw him that one. 11 goes to 8. Okay, that's a Bob. I'll throw him that one. 11 goes to 10. Okay, that's a Bob. I'll throw him that one. And oh, 11 goes to 7. Oh, that's a Dan. I won't give him that one. So the software could handle that as it searched the table. So it could use the duplicate table to handle hash collisions as well. And I'm sure there's people that do this every day. This is their profession, who have more elegant ways to handle a collision rather than checking each one. But you can see that duplicate names and collisions can be handled. We just have to have a separate table to handle our duplicates and collisions. We can do that with one table. There might be better ways. So that's a lot of information I've thrown at you. So let's go through this process again to see how we would use a hash table. And I'm going to leave all the information up here. And just for the fun of it, I'm going to throw in one more new person. Let's do Mark. Now Mark, I hashed that out. Okay, take the ASCII code for that, add that to the ASCII code for that. If it comes out over 100, throw out the 1, blah, blah, blah. Mark ends up coming out 99. That's the highest number I can have if my limit is decimal numbers and I can only have 100 entities. Now in reality I can be more flexible than that, but I'm trying to show this with decimal numbers to help us understand it. So Mark comes out 99. So we go down all the way to the bottom of the table and we have number 99, and that's going to go to Mark. Let's get Mark out of the way here. Mark is in our table here, and he's going to be number 11 in the table, so 99 goes to 11. Now, if I go search for Mark, now Mark is at the very bottom of the hash table. So if I use this hash table such that I had to search it, I'm going to have to go through the whole hash table before I find Mark. Now, of course, if these are in numerical order, I could do a divide and conquer search, which would speed that up by an order of magnitude. But this is a little wasteful in memory, but I think the speed gain by using it this way would compensate for the fact that it's a little wasteful in memory, because no matter what you do, you're going to end up with empty spots in the table, but who cares? So I go and I search for Mark. I want Mark, okay? The database goes to Mark, hashes it, comes out with the number 99, multiplies that by 2, goes to here, adds 198 to that, comes down to here, sees that's 99, and then goes to number 11, and there's Mark. So this speeds up the search tremendously by not having to search anything, because all I do is hash it, multiply it, jump down. And you might be realizing, what the heck do I even have to store the hash for? Because the hash becomes the address. So let's go ahead and that saves a whole byte of memory. And now in this case, I don't even have to multiply the number. Let's get rid of these. Because since I only have 100 entities, I only need 1 byte to store my my pointer here. And so that's going to be memory address 1000, 1001, 1002, and etc. This was 17, so that's going to be 1017. That's going to be, don't need that anymore, 1099. So it's just 1 byte, 1 byte, 1 byte, 1 byte, 1 byte. That even makes it easier. So now I'm going to look for Paul. So I type in Paul, and the program says, oh, you want Paul? Let me hash that. So Paul comes out to number 6. So it hashes Paul, gets to number 6. Doesn't even have to multiply anymore. Just goes to 1000, adds 6, points it right there. 6, oh, how convenient. 6 goes to number 6 over here, and there's Paul. So I don't have to do any search. I just do the hash algorithm. Let's do that one more time. Let's look for Zeke. Zeke hashes out to 3. So I type in Zeke, the computer hashes it, gets to number 3, goes to here, adds 3, 1, 2, 3, and then Zeke goes to 3, and once again the coincidence of the hash is the also points to the row. So hash number 3 goes to row number 3, and there's Zeke there. And so I hope you're following what I'm doing here. Let's just do one more. Let's look for Bob, because Bob has a slight problem here. So Bob. Now I'm going to search the database. I want Bob. The database hashes that out to number 11. So it goes to here, adds 11, so jumps down to number 11, which points down to here. And there's a code that says, uh-oh, I'm just going to put an X here. We have either a duplicate or a hash collision. So we have to go to the dupe table. So, okay, there's number 11 goes to 4, that's Bob. Number 11 also goes to 8, that's Bob. 11 also goes to 10, that's Bob. And number 11 goes to 7, but that's Dan. We don't want Dan, so there's your 3 Bobs. So that's how a hash table works as I would implement it. And let's step back a minute, because if you research hash tables, you'll see that they say that they store a hash and value pair. I have removed the hash from the hash table because the hash is the address. I don't need to have the hash to find the value. But it's possible to implement a hash table where I have the hash value, hash value, hash value. And in that case, I would have to search the table for the hash. And if I put them in numerical order, I could do a divide and conquer search and speed that up. That would be more efficient. Wouldn't have empty slots in the hash table, but then I have to search the hash tables. To take your pick, which would you rather do? Would you rather search a hash table with no empty slots, or have a hash table that doesn't need to be searched? I just take the hash, jump down, there I am. So there is how I would implement a hash table. So I hope you found this video useful and informative and not too confusing. I hope that made some sense to you. And if you did find this useful and not too confusing, please give me the thumbs up below. It really helps other people find this video. And be sure to subscribe, hit that gray bell when you do. A big thank you to my supporters. You are making this possible. And thanks to everyone for watching.